In this video, we will briefly discuss about linear algebra required to study quantum mechanics and to understand concepts in quantum computation. So let's start with the video. Linear algebra is the study of vector space and of linear operations on those vector spaces. The vector space we are interested in is the space of all n tuples of complex number z1 to zn represented by c raised to n. The element of vector space are called vectors and sometimes represented by column matrix notation. We define the addition of vectors by this operation on Cn space, and we also define the scalar multiplication of vectors by a scalar A, which is a complex number on a n-dimensional complex vector space by this operation. Quantum mechanics is our main motivation for studying linear algebra. In quantum mechanics, a state is represented by a state vector given in Dirac notation by ket psi. If you want to know more about the Dirac notations, click on the I tab to watch the video. A vector space also contains a zero vector denoted by this 0. We are not writing this 0 vector in this notation since this notation has altogether different meaning in quantum computation as it represents a 0 state qubit. This 0 vector satisfies the following addition and scalar multiplication rule, where v is our vector in our complex vector space and z is a complex number. A basis of an n-dimensional vector space Cn is a set of linearly independent state vectors v1, v2 to vn such that any state vector v belonging to Cn can be written as this expression, where the coefficient a are all complex numbers. That is, any vector v can be expressed as a linear combination of the basis vector. Here, we'll define the linear independence in some times. The basis set is also called spanning set since all the basis vector linearly spans the entire vector space. For example, for a vector space in R3, our basis vectors are x, y, and z coordinates if you are talking in Cartesian coordinates, such that any vector in R3 can be expressed as a linear combination of these basis vector x, y, and z. That is, any vector A can be written as a linear combination of our basis vector. For another example, let's take a vector space C2 such that the basis vectors are x1 and x2, where x1 is equal to 1 0 and x2 is equal to 0 1. So any vector v which is given by its coefficient a1 a2 can be written as a linear combination of x1 and x2 such that v would be equal to a1 into 1 0 plus a2 into 0 1. This is equal to a1 into x1 plus a2 into. So I hope you understood what are basis vector and how they span a vector space. Now let's see what are linearly independent and linearly dependent vectors. A set of vectors v1, v2 to vn belonging to a vector space V is said to be linearly independent if there exists a set of complex numbers a1, a2, an such that a1 v1 plus a2 v2 till an vn is equal to 0 for all ai equal to 0, and if any one of this ai is not equal to 0 for this form, then the set of vectors are linearly dependent. What this equation says is, if any vector vi is dependent on any other vector vj, then the ai and aj corresponding to those vectors will be a scalar multiples of each other, and the set of vectors will be linearly dependent. Example, take two vectors v1 and v2 such that v1 is equal to 1 2 and v2 is equal to 2 4. Then we can write v2 is equal to twice of v1, which is equal to 2 4, which implies v2 is a dependent or a redundant vector in the given vector space. In conclusion, we can say that linearly dependent vectors are redundant and do not add dimensions to the span of the linear combination, whereas linearly independent vectors add another dimension to the span of the linear combination. So I hope you understood what are linearly dependent and linearly independent vector sets. A linear operator A which maps on the vector space V to V is defined to be linear in its input, which is given by this expression. We can opt to write a vj as simply avj also. The two important linear operators are our identity operator I and the zero operator, where I operating on V gives us the same vector and 0 operating on V gives us the 0 vector, where it maps all the vectors in the vector space to the 0 vector. Now for three vectors V, W and X, such that A maps from V to W and B maps from W to X are our linear operators. Then BA denotes the composition of B with A, defined by BA operating on V gives us B operating on the state which we get when we operate A on V. This operation BA map from V to X. Now every linear operator has a metric representation, that is A can be represented in its matrix form Aij. Suppose A is an operator which maps from V to W vector space, where V1, V2 till Vn and W1, W2 till Wn are the basis of these two vector space, which implies A operating on Vj will be equal to summation I Aij Wi for all I from 1 to n and for all j from 1 to m, where we know Aij are the entries of the matrix representing the operator A. You can click on the I tab to watch the matrix representation of different operators video. Now let's see what are polymatrices. These are set of 4 2x2 matrices which are very important in quantum mechanics and also in quantum computation. These are represented by sigma 0, sigma x, sigma y, sigma z, or we can also call them as x, y and z, and sigma 0 is our identity matrix. These matrices are also called polyspin matrices. In quantum mechanics, these matrices are used to describe particle spin in different directions with the basis of plus or minus 1. Now before we see what are inner products and outer products, let's recall that a ket psi is represented by a column matrix and its dual vector bra psi is represented by a row matrix. Now knowing this, let's define an inner product. An inner product xy is a map from vector to scalar that satisfies the following linear properties, where x, y and z are our state vectors. The inner product of x with z plus y gives us x inner product z plus x inner product y, and x with inner product y acts linearly with a scalar multiple. Also, x inner product y is equal to y inner product x with a complex conjugate, and for all x not equal to 0, x inner product x is always greater than 0. Here we have used the standard inner product notation. Another way to define an inner product is with this notation. This notation is not a standard notation. It is just a function with two vector inputs represented by this symbol. We can also define an inner product in this notation as a function from v cross v to a complex number is an inner product if it satisfies this argument. That is, this function is linear in the second argument. As you can see, a scalar lambda I is linear. Second, Vw is Wv with a complex conjugate, as we saw in the previous definition also. And third is V inner product W is always greater than 0, and this would be 0 only if V is equal to 0 or W is equal to 0. Now let's see a working example of inner product in standard notation. Let's take a vector x given by a column matrix x1 till xn and another ket y given by column matrix y1 till yn. So the inner product of xy would be equal to x1 star x2 star till xn star. Since now we have transformed the x to its dual vector bra, which is the complex conjugate transpose of this ket x, therefore writing it in row matrix multiply with y y1 till yn. Now this matrix multiplication gives us a complex number summation I xi star yi, which is a complex number. Now similarly we can define an outer product as x y in this notation, which would be equal to x1 till xn, and since now y is in the dual vector space, it would be written in the row matrix y1 star till yn. Now multiplying these two matrices, we'll get a matrix x1 y1 star till x1 yn star xn y1 star till xn yn star. So an outer product gives us a matrix as a result. Another example we can take is of a zero state which is given by 1 0. So 0 outer product 0 would be equal to 1 0 1 0, which would be equal to 1 1s are 1, 1 0s are 0, 0 1s are 0, 0 0s are 0 in this matrix. So I hope you understood what are inner products and outer products. Now let's see what are eigenvalues and eigenvectors. For a 2D vector, its span is a line, and for a 3D vector, its span is a plane. So when a linear transformation is done on a vector space, most vectors get knocked off their span, but only few special vectors remain on their span. These vectors are called eigenvectors, and the scaling that happens on them on the span is called their eigenvalue, given by this equation. So when this operator operates on this eigenvector, they only scale them by lambda times, and by solving the determinant a minus lambda I equal to 0, we get the eigenvalues, and further with those eigenvalues we can calculate the corresponding eigenvectors. The tensor product is a way of putting a vector space together to form a larger vector space. Let V and W be a m-dimensional and n-dimensional vector space with elements vi's and wi's. Then V tensor product W is a m n-dimensional vector space and the elements are vi tensor product wi. We can also write the tensor product V tensor product W in another notation as v w or v comma w, or just simply v w. These all represents a tensor product operation. By definition, tensor product satisfies the following basic properties, where z is a complex number, vector v belongs to the vector space V, and vector W belongs to the vector space W. So as you can see, our tensor product operation follows the linear property of scalar multiplication. Also, it follows the distribution property, as you can see from these two equations. Now, for a vector space V tensor product W, where V belongs to V and W vector belongs to W, we can define a linear operator A tensor product B as when A tensor product B operates on an element of this vector space V tensor product W, we get A operating on vector V tensor product B operating on vector W. And this definition of A tensor product B is extended to all elements of this vector space, such that A tensor product B operating on any elements of this vector space with a scalar multiple AI gives us this product, where A operates on Vi and B operates on Wi. Now let's take two operators A and B, and we know all operators are represented by a matrix, so A will be represented by Aij matrix and B would be represented by Bij matrix. Then A tensor product B would be equal to a bigger matrix given by this m cross n matrix. Let's take another example where A is a 2 cross 2 matrix 1 0 0 2 and B is a 2 cross 3 matrix 1 2 3 0 4 7. So A tensor product B would be equal to, from this general matrix, each element of A would multiply with the matrix B. So it would be 1 times B, 0 times B, 0 times B and 2 times B. Here these scalars are multiplied with each element of this matrix B. So this would give us a bigger matrix. When 1 multiplies with B, we get 1 2 3 0 4 7. Similarly, when 0 multiplies with each elements of B, we get 0 0 0 0 0 0. And again, when 0 multiplies with B, we get. And finally, when 2 multiplies with B, we get 1 2s are 2, 2 2s are 4, 2 3s are 6, 2 zeros are 0, 2 4s are 8, and 2 7s are 14. So we get this bigger metrics. So I hope you understood what are tensor product and their operations.